In this presentation, I'm going to talk about the breakthroughs we've achieved in silicon carbide power MOSFET technology at NC State under the sponsorship of PowerAmerica. I want to begin by pointing out two key contributors to this work. First is Dr. Woonjae Sung, who worked with me in BP1 and BP2 while he was here at NC State as a research professor, and then he has since then moved to SUNY. The other is Ki-Jong Han, my PhD graduate student, who has done an exceptional job in making a lot of these ideas a reality, and a lot of success that I'm reporting is because of his hard work. I want to, of course, acknowledge the support we've received over these years from X-FAB. All the devices I'm going to speak about and the processes have been run at X-FAB, and we have been privileged to work with them in a manufacturing environment. So the outline of my presentation is shown here. As you can see, I have a lot of material to cover, and so let me begin by covering the first topic, which is PRECISE. PRECISE stands for Process Engineered for Manufacturing Silicon Carbide Electronic Devices. With this process, we can make the devices shown on the slide, including the JBS rectifier, the power MOSFET. In the case of the power MOSFET, we have two types of structures, one with an inversion mode channel and the other with an accumulation mode channel. Our accumulation mode channel devices have a channel mobility which is almost as good as the inversion mode channel and is therefore better in terms of RDS on. Then we've also created a device we call the JBS-FET, where we've integrated the JBS diode into the MOSFET. And finally, I want to talk at the end of the presentation about a bidirectional FET, which combines JBS-FETs for that function. So in terms of the PRECISE process, we have spent a lot of effort to qualify the process by defining a process flow at NCSU to manufacture silicon carbide MOSFETs, JBS-FETs, and JBS rectifiers at X-FAB. We designed a mask set for this purpose and provided it to X-FAB, and they ran 3 process lots for the qualification. The wafers came back to NC State, and we did extensive testing to get statistical data, and I'll be showing you wafer maps and statistical distributions. We were looking for parametric distribution within each wafer, from wafer to wafer, within a process lot, and also from lot to lot. All this data acquisition was performed by using a semi-automated Signatone wafer prober and Keysight test equipment. Before we could make any devices, power devices, we needed to make sure we had a good, robust, high voltage edge termination. So we did an extensive study of various techniques to create the edge termination. This included the single zone JTE, the ring assisted JTE, the multiple floating zone JTE, the hybrid JTE. And you can see from this chart that among all of these, the hybrid JTE, the orange line, has the broadest spread, meaning it has a lot of wide process latitude and it's easier to fabricate. And it also gives nearly ideal breakdown voltage. We did some early work in BP1 to compare the floating field ring with the multiple floating zone JTE, and you can see from this chart that the breakdown voltage with multiple floating zone is 1250 volts compared with only 870. But things got even better once we introduced the hybrid JTE. And with this termination, you can see that with the inversion mode MOSFET, we get a very low leakage current, and the breakdown voltage is 1730 volts for our devices. The breakdown voltages are usually specified at 100 microamps, but the leakage current here is very low in the nanoamp range. In the case of the AccuFET, the leakages are larger, but they're still well within the 100 microamp spec, and the breakdown voltage is about 1650 volts. So turning to the PRECISE process and its qualification, I'm going to start with the 1.2 kV JBS rectifier. Again, this device was qualified with 3 process lots at X-FAB. The devices were made by using nickel as a Schottky contact, and the size active area of the device is 0.046 centimeters squared. This picture shows, slide shows a picture of our 6-inch silicon carbide wafer from X-FAB. So in terms of the Values, we are showing you wafer maps for the on-state voltage drop here. In addition, at the bottom, you can see the statistical distribution. And the conclusion is that the average value is about 2 volts for the forward drop on our diodes, and the distribution is very tight. The standard deviation is quite small. The leakage current can be a challenge for Schottky rectifiers, and this requires proper design of the JBS-FET structure and a good process for making the nickel Schottky contact. We have achieved this, and we have low leakage currents in the nanoamp range, and the values are all well below the leakage current of 100 microamps. So our yield is generally more than 90%. In terms of lot-to-lot variation, this slide shows wafers from 3 lots, and once again, the distributions are very tight, and we have good reproducibility. Same holds true for the leakage current. The leakage currents are also in nanoamp range for all of these wafers, and well below the 100 microamp spec. I'm now going to turn to the qualification of the MOSFET. Here, I'll focus mainly on the AccuFET because it has better RDS on, and these devices have an active area of 0.045 centimeters squared. I want to point out that when we measure these devices on a probe station, we experience a parasitic resistance of about 35 milliohms, which translates to about 1.6 milliohm centimeters squared as a specific resistance. In addition, of course, the substrate itself contributes about 1 milliohm centimeters squared. In addition, there is a small parasitic capacitance of 0.5 puff in our CGD measurements. So this chart shows the distribution of on resistance across 2 wafers. You can see a lot of blank spots. Unfortunately, when the testing was being done initially, there was some arcing experience, and we lost a lot of devices because we were not using fluoriner. Since then, we have remedied this, and we are now no longer experiencing a problem. So what the data shows here is that the average value for all the wafers in all the lots is 144. So for these particular wafers, you can see the numbers on the chart, and the distribution is also very tight. So I want to convert these numbers into a specific resistance because many of you like to know that. So using the active area from the previous chart, it works out to be 6.5 milliohm centimeters squared. If you take away the probe resistance, then this would be 5 milliohm centimeters squared. If you proceed to thin the substrate, then it is possible to bring this down to about 4.5 milliohm centimeters squared. The threshold voltage of our accumulation mode device is positive. There's sometimes a misunderstanding that people think accumulation mode devices are depletion mode devices. They are not. They are enhancement mode devices. They have a positive threshold voltage, as you can see here, of 2 volts average for one of the wafers and 2.48 for the other wafer. These values, again, fall within the kind of distributions we see in data sheets. In terms of the capacitance, we have monitored all the different types of capacitances, but I want to stress CGD because it's a measure of the switching speed and losses. So the CGD is usually quantified as VD of 1,000 volts in data sheets, so that's what we have given here. And you can see again the distribution is very uniform and has a very small standard deviation. In terms of leakage current, these devices have the leakage currents in the nanoamp range, and if you look at the distributions, they all fall, the values all fall below, well below 100 microamps. Turning to lot variations, you can see here 3 wafers from 3 different lots, and you can see again the average values are given on the screen, and they fall in a pretty tight distribution. Our threshold voltages are also very uniform from lot to lot. And the CGD values are also very uniform from lot to lot. Finally, if you look at the leakage currents, they all remain in the nanoamp range among all the devices. So as a consequence, the yields tend to be in the 90% plus range in this process. So the results obtained here are a combination of robust chip design as well as, of course, very good process flow that is run at X-band. Turning to the inversion mode MOSFET, I want to say that these have also been qualified, but in the interest of time, I'm not going to repeat and show you all the qualification data. If anyone has interest in it, they can approach me. So this technology is available for licensing from NC State for manufacturing products of X-FAB. One company has already licensed the technology and is building product at X-FAB at this time. And we have several others showing interest. So continuing with my outline, I want to now talk about the JBS-FET. The innovation here is that we have integrated a Schottky diode into the silicon carbide MOSFET structure. The way we do this is shown on this slide, where the upper part shows the conventional MOSFET structure. And in the conventional MOSFET structure, when you operate it in the third quadrant, the body diode turns on, and you get bipolar current flow due to injection of holes from the P+ region into the drip layer. That's for the upper device. In the case of the JBS-FET, we have opened up the body region and introduced a Schottky contact. This allows us to create a JBS diode which works together with the MOSFET structure. And the JBS diode is actually in parallel with the body diode, and because of its low VF, which is designed by us very carefully, we can completely clamp current flow in the body diode. So this avoids bipolar current flow through the body diode and greatly improves, of course, the switching performance, especially at high temperatures. In terms of the JBS-FET design, we've taken several approaches. One of them was shown in the cross-section in the previous slide, but we have looked at several other approaches as shown on this slide as well. So to begin with, let me talk about the first row, which is what you could do by taking two separate devices, a power MOSFET and a JBS rectifier in a separate package, and then connect them together. When you do this, you incur a lot of area loss because of the edge termination for both devices, as well as space for the scribe lanes, and the total area works out to be 0.0707 for these particular designs with 5.7 amp capability. In our first approach, which was shown in the cross-section in the previous slide, we can reduce the net area down to 0.04, so you get a substantial reduction of silicon carbide area, which of course translates to lower costs. We have also looked at two other options, which is to combine the JBS-FET with dedicated areas for the JBS diode on the same chip, and that's shown in the third and fourth row, the two different ways of achieving the same function. All of these approaches are compared in terms of area savings over here. In the interest of time, I'll just say in conclusion, we are able to achieve an area savings of about 40% by using the JBS-FET approach. And of course, we get the additional benefits of cutting the number of packages in half, and we eliminate any parasitic inductance between the diode and the MOSFET. The JBS-FET process flow is shown here. This is the process flow we have implemented at X-FAB. It's a very basic process flow, which is probably used by most people in the industry. So in our process, we do all the ion implants first for all the layers, then the activation and needle is done after that. This is followed by gate oxidation, and then we deposit gate poly, and then we intermetal dielectric, and finally we do the metallization, including the ohmic and the Schottky metal. One of the innovations we have done here is to develop a process by which we can simultaneously form a Schottky contact to the drip region and form an ohmic contact to the P base as well as the N+ source. And that is very important in terms of process convenience as well as chip design. So after that step, we do a thick top metal and polyimide passivation, and this is followed by the backside metal process as well. The very first data that we obtained, which I call Gen 1 back in BP1, is shown here. On the right-hand side, we show the third quadrant behavior, and you can see that the JBS FET works as expected with the JBS diode kicking in, and we get 5 amp current flow with a voltage drop of only 2 volts. In comparison, when we measure devices without the integrated diodes, the MOSFETs here you can see have a VF of over 5.5 volts. So these are the body diodes of MOSFETs. On the left-hand side, the output characteristics of the JBS-FET are shown in the first quadrant. The early devices had high on resistance of 20 milliohm centimeter squared. Since then, we have improved upon the on resistance with cell optimization, and I'll be showing you that data. So we have done process qualification for the JBS-FET. In our JBS-FETs, we chose to use the accumulation channel because it has a better channel mobility, and by doing this, we were able to get good performance, which I'll be sharing with you next. So here's the data on 3 wafers from 3 different lots. Again, in the interest of time, I've cut down the number of charts on the process qualification. So here you see the AccuFET resistance for 3 wafer lots. The resistance here is higher than that of the transistor alone because of the integration of the diode. The distribution of resistances are very tight and uniform. The specific resistance for this design works out to be 11.2 milliohm centimeters squared. Again, that is actually translated to 9.6 milliohm centimeters squared if I remove the probe resistance, and if we were to thin the substrate, this would come down to about 9.1. The threshold voltage for these lots is running about 2.4 volts among all of them, and you can see from the chart in the lower part, the distribution is tight and the standard deviations are small. Of course, the main attribute of the JBS-FET is the third quadrant behavior. So you can see that here for 3 wafers from 3 lots, and you can see that the voltage drop in the third quadrant is in the 2 volt range and it's very tightly distributed. The other important thing to note is that the leakage current of the JBS-FET is very good in spite of integrating the Schottky contact. This is by a combination of good design of the JBS contact area as well as the process used to make the chip. And the leakage currents for these devices are also in the nanoamp range, well below the 100 microamps. So this technology has been qualified, and if there is any interest in licensing, you can contact me at NCSU. Now I want to move on to the optimization of the JFET to improve the on resistance and improve the high frequency figure of merit for the devices. So in terms of the device structures, if we increase the doping in the JFET region, you can shrink the space, and that reduces the contribution from the channel because of the increase in channel density. In addition, making the space smaller reduces the capacitance between the gate and drain of CGD. We also want to use a small cell pitch to increase channel density, and we've achieved this by making the contact to the P-body orthogonal to the cross-section as mentioned here. So using these approaches, we can bring down the specific on resistance as well as the CGD, as I'll show you next. So this is a chart comparing the conventional MOSFET and this new design with the JFET doping. So the upper part shows the results we obtained in BP1 with the conventional design. With that, we had an RDS-on of 8.46. This includes these parasitic resistances. And then we had a CGD of 0.2 and a QGD of 391. By using the new structure with the JFET doping and orthogonal contact, the RDS-on went down substantially, and so did CGD and QGD. So this results in a big improvement in the figure of merit, which I've defined in 2 ways. One is the product of R and C, and the other is the product of R and Q. The numbers for BP1 are probably similar to Gen 1 MOSFETs that were being sold by the industry. The numbers here are closer to the Gen 2 MOSFETs without subtracting these contributions. If you subtract the probe resistance then our numbers turn out to be a little bit better than what we see in our Gen 2 devices. So once again, this technology is available for licensing if it's of interest to you. Now I want to talk about two key innovations that we've made, which have made significant improvements in the high-frequency figure of merit. The first of these is a device I call the split-gate MOSFET, or SG MOSFET. So in this slide, I compare the cross-section of the conventional device with the split-gate device. As you can see in this structure, what we have done is remove a portion of the gate which overlaps the JFET region. By removing that portion of the gate, we reduce the capacitance between the gate and drain and improve the capacitance and QGD. So these devices can be fabricated with the same process flow as the conventional device. So this is an advantage of the structure. It merely requires redesigning the gate region for mask layout. So here we show you our analysis of the structure using computer simulations. What we're trying to do is to determine the impact of performance on this X parameter. The X parameter is defined as the extension of the gate beyond the edge of the channel or beyond the edge of the P+ shielding region, which is below the channel. So you can see that as X expands, a lot of changes occur. I should point out that the JFET width in our design has a value of 0.9 microns, it's right here. As a consequence, when X becomes equal to 0.9 microns, we end up with a conventional structure. So if we reduce X, then we start getting lower and lower values for CGD as expected, and QGD, of course, also goes down. And this results in significant improvements in switching behavior. But we have to also monitor the RDS on and the oxide electric field. So in terms of RDS on, as X is reduced, the accumulation layer at the top of the JFET region becomes smaller, and the RDS on does start increasing, so we have to be careful about that. And we have to also worry about any electric field enhancement at the edge of the gate. And you can see here that we have monitored it over the various values of X. Based upon these results, we believe that the optimum value for X was 0.3 microns because that's something we could fabricate at XFAB. I'm going to show you results achieved with that value. So here's the experimental data on devices made with the split gate structure and the regular structure. You can see from the output characteristics that there is very little difference between them. The same holds true for the locking characteristics, which tells us that the oxide electric field is also reasonable and low. The big improvement, of course, occurs with the capacitance. So this is the CGD that I'm showing you in this chart. And usually CGD is given at 1,000 volts, and at 1,000 volts there is a small improvement. But what you have to note is that at small drain biases, there is a very large improvement, almost 1 order of magnitude reduction in CGD. And this is what translates to a much smaller QGD for the split gate devices. So here's a summary comparing the performance of the SG MOSFET and the conventional MOSFET as measured in the devices that were fabricated at XFAB. You can see the breakdown voltages are about the same threshold voltage. RDS on is also very close, but we have a big reduction in CGD at 0 volts and also a reduction in CGD at 1 kV. Significant reduction in QGD as well. So if you apply this and calculate these various figures of merit, you find that you get a 6x improvement in the RC figure of merit if you use the 0 VD value, and a 1.3x improvement if you use the 1 kV value for CGD. If you use the QGD values, then you get an improvement of 2.4x. So this technology and design is available for licensing from NC State as well. Next device I want to talk about is the buffer gate MOSFET. This is a structure that makes even further improvements in the high frequency figure of merit than the SG MOSFET. here's a comparison of the buffer gate design with the split gate and the conventional MOSFET. So since you just saw what happens in the split gate MOSFET, it's best for me to compare the buffer gate device to the split gate device. So this device also has a split gate. In other words, we've removed the polysilicon in this portion. But what's different is that we've extended the P+ shielding region beyond the edge of the gate region. So in this case, the P+ shielding region is on the left side of the edge of the gate. Here now the P+ shielding region is extended to the right side. By doing that, we get exceptionally good shielding of the gate from the drain, or buffering of the gate, and that significantly reduces the capacitances as well as the gate charge. Now, one of the things that you have to watch out when doing this is that if you don't enhance the doping in this portion here, then the built-in potential of the p-n junction will deplete this part, and you will end up with very high on resistance. So we had to introduce an additional JFET doping to achieve proper functionality. So the first optimization we did is to find out the highest JFET doping that we should use, or the right value of JFET doping that we should use. I should mention that if you use too high a JFET doping, then the electric field at this corner goes up and you might end up with bad breakdown. So you can see here in this chart that as the JFET doping concentration is increased, we see a reduction in RDS on because this region is no longer pinched off and it settles down to good values. But if you keep increasing the doping, then the oxide electric field starts getting very low, and that is not good for reliability. So we believe that the optimum JFET doping concentration lies right here at 3E17, which gives us very good on resistance, and we still have low gate oxide electric field. In terms of capacitance and QGD, you can see a rather complex plot here which shows what happens when we fix X1, which is this dimension, at 0.4 based upon alignment tolerances and the FAT, and then we look at what happens with X2 being changed. Now, we have defined X2 as the amount of extension of the P+ region beyond the edge of the gate. So positive values of X2 show this extension, and that is representative of the BG MOSFET. When X2 becomes negative, the gate is now extending into the JFET region, and that is actually like the cut gate device or split gate devices over here. I'm going to focus here on the BG MOSFET, and you can see here that as X2 is made larger, in other words, the P+ region is going further and further out, we're getting a big reduction in CGD and QGD. The thing again you have to watch out with this design is that if you make this P+ wider and wider, then you get more and more resistance from this portion, and the RDS on starts going up. So if you include the impact of the change in RDS on and the values for CGD, QGD, you get these figures of merit, and you can see a very substantial reduction of the RQ and RC figure of merit with this structure. So in terms of fabrication, we found that an X2 value of 0.3 microns was the best choice based on alignment tolerances at X-FAB. So we fabricated devices using X1 of 0.4 and X2 of 0.3. These are the experimental results. In terms of devices, we made both inversion mode devices and accumulation mode devices as far as the channel is concerned. And here you can see that the accumulation mode device, the blue, is slightly better than the inversion mode device in terms of RDS on. In terms of breakdown voltage, we get very good breakdown voltage for the conventional MOSFET, the blue line, the SG MOSFET, and of course the accumulation mode BG MOSFET. However, we found that our inversion mode BG MOSFETs had poor breakdown voltage of about 500 to 600 volts. We did a lot of investigation into the cause of this, and it has to do with the particular implant profiles. You can find this discussion in one of our published papers. In terms of the capacitance, you can see that there is a big improvement in the CGD at high voltages as well as lower voltages by using the SG MOSFET structure. And this improvement, this reduction, translates to a very, very low value of QGD. So this is an exceptionally low value of QGD, which gives us very high figures of merit as shown in this table. So this summarizes all the experimental results for the conventional MOSFET, SG MOSFET, and two types of VG MOSFETs. The VG MOSFET L had a slightly lower doping concentration for the N plus JFET region, and this one had a slightly higher doping concentration. In both of these devices, cell pitches are bigger than the conventional SG MOSFETs because of the way the structure is designed. The breakdown voltages obtained are comparable. The threshold voltage is also very close, but because of the larger cell pitch and additional resistances, we do have higher RDS(ON) for the VG MOSFET. However, there is a huge reduction in the capacitance, as you can see from these values, and a big improvement in QGD. So this produces a net significant enhancement in the figures of merit. So for the RC figure of merit, we see an improvement of 3.6x, and for the RQ figure of merit, we see an improvement of 4x. So I feel that this kind of a device is very good for using these MOSFETs in higher frequency applications. And since the target market for silicon carbide devices is to displace IGBTs and increase switching frequency so that we can reduce the size of parasitic elements in power electronics, I think devices like this may help us promote these devices in markets. This technology is also available for licensing from NCSU if anyone has interest. So my last topic is going to be an innovative device which I have proposed called the monolithic bidirectional field effect transistor, or BIFET. This idea was based on a need for improved devices in cycloconverters or matrix converters. The review paper I cited here says that a matrix converter creates a variable output voltage with unrestricted frequency using an array of fully controlled 4-quadrant bidirectional switches as the main power elements. And it does not need any large energy storage elements or DC link circuit. As a consequence, this ends up being a much higher power per unit density performance. The authors also state that unfortunately there are no such devices. These devices available, and consequently multiple discrete devices have been used to construct each of these switching cells. And that, of course, makes the topology more complex and increases its size and weight. So the proposed idea is actually very simple in concept. It takes two JBS-FETs, which you heard about earlier in my presentation, and marries them on a single chip. And they share a common drain. So this is a single chip as envisioned here with 4 terminals. So we would use T1 as a reference terminal and T2 as a high voltage terminal, so that you apply both positive voltage here for first quadrant operation and negative voltage for third quadrant. The device would then have 2 gates, G1 reference to T1 and G2 reference to T2. So the details of the JBS-FET are shown here, and as you can see, we have the integrated JBS diode, and I've included the edge termination to emphasize that both of these chips have their own separate edge terminations. So if you take this concept, we can realize it by using the JBS-FETs that we have manufactured at XFAB, and this is data taken on our devices. So if you use T1 as a reference and apply positive bias to T2, then the JFET1 supports the voltage. In JFET2, the body diode becomes forward biased. You can see here that the device is then capable of blocking 1650 volts, as I showed you earlier for JBS-FETs. And the leakage current is very low in spite of our Schottky contacts. If you turn on the gate G2 and apply 25 volts, then you turn on the channel of this device, and you then can apply various gate biases to G1 as shown over here, and obtain fully gate-controlled output characteristics. And the resistance of the device is a combination of the resistance of this device plus the resistance of this device. So In the example I'm showing here, we have a total resistance of 0.5 ohms, which can, of course, be greatly reduced by increasing the size and area of each of these devices. These devices have excellent output characteristics and good safe operating area because they are based on silicon carbide MOSFETs. If we do not turn on the gate bias to G2 and only apply gate bias to G1, then you get these characteristics. The key difference is that now we have a knee. This knee is created by the current flow through the JBS diode for the JBS-FET2, and beyond that, the rest of the characteristics are controlled by JBS-FET1. So I wanted to briefly compare this to the prior art approaches used by people to make devices for the matrix converter. There are 3 silicon approaches, all using IGBTs. All of these use IGBTs. These 2 use a symmetric blocking IGBT and put a diode in series. As a consequence, the on voltage becomes high, as shown here. These voltages are based on the assumptions given below. And you also end up with a large number of packages and devices. You can reduce the number of devices by using reverse blocking IGBTs, and there are a few available. The problem with them is that the switching losses for reverse blocking IGBTs are much, much higher than for the asymmetric or symmetric blocking IGBTs. And their on voltage also is larger. Of course, we can also implement this with silicon carbide devices, and two references, case D and E, have done this. In these approaches, we suffer the consequence of multiple devices and packages, and the on voltage works out to be 1.75 volts because the current flows through the MOSFET and the diode. The device that I have proposed allows reducing everything down to a single 4-terminal package, and we expect to get a VF of 0.5 volts by scaling the size of the MOSFETs. So, in summary, this is a new device targeted towards matrix converters, and we're in the process of now developing a program to build larger devices and then show their performance inside a matrix converter. So this technology is also available for licensing from NC State if there's any interest. So in conclusion, I've shown you a number of breakthroughs that we've achieved in silicon carbide MOSFET technology at NC State. If there's any interest in commercialization, you can contact me at the email address given below. And I want to start by acknowledging, of course, the support of PowerAmerica for achieving these breakthroughs in silicon carbide MOSFET technology. Thank you.
Thanks very much, Jay. That was really a pretty significant body of work, and you have a lot of great technical achievements, and really appreciate your time today. Okay, we have time for questions, so please use the chat function in the upper right corner of your screen to type in your questions to us, and I'll read them off, and then we'll respond. Jay will respond verbally. Are there any questions from anyone on the line? Okay, the first question is, are listed pitches full or half pitch?
So the dimensions were shown on the slide, and they are for the cross-section shown in the slides. That's the best way for me to answer it. If you want, I can go back, I guess, in my slides. What about? So I think you're referring to a slide like this. So here the pitch is given, and the pitch, all the dimensions are given. So it's for this cross-section. So I guess I would call it half pitch or half cell.
Thanks. The next question is, what happens when both gates are off and T1 or T2 is at high voltage in the bidirectional device?
Okay, I'm going to turn to the slide that shows the device and its performance. Okay, so in this case, we have applied a zero bias between G1 and T1, otherwise it's shorted. G2 and T2 are also shorted. So now if you apply a high voltage, positive voltage here, this body diode will get forward bias, but this device will get reverse bias, this diode will get reverse bias, and this MOSFET will work in its first quadrant and support the high voltage as shown here. If you apply a negative voltage here, now this body diode will get forward bias, and this MOSFET will support high voltage, and you'll get exactly the same characteristics in the third quadrant, which I'm trying to show by using my mouse and highlighting. So hopefully that makes it clear.
Thank you. Okay, any more questions? Someone is typing, so we'll give them a second. Typing very slowly. Okay, a follow-up question. Is there any danger of voltage floating?
I assume you're talking about the BIT-FET?
I think it's the same questioner, so it's probably related to the same device, yeah.
There is no floating voltage because all the connections are shown here in the cross-section. So each of these devices, the one on the right-hand side, JBS-FET2 and JBS-FET1, function exactly like in MOSFETs that we have today, and there are no floating regions. The edge termination is also connected to the terminal T1 here and T2 over here. So you can look upon this as two MOSFETs that are combined in series. What's unique is that I've taken advantage of the fact that on our chips, the MOSFETs share a common drain and drip layer as a substrate. So I've taken advantage of that to make a simple four-terminal device.
Okay, are there any more questions? Going once, going twice. Okay, I guess we'll end it. Thanks again very much, Dr. Baliga, and thank you all again for joining us today from PowerAmerica. Have a great day.